Welcome everyone. If you're coming here from the previous video, you'll remember that we talked a ton about GD&T. My goal in that video was to really make a case for learning GD&T. This is chapter 2 of the GD&T series. If you're just joining and you want to know what GD&T is all about, I really suggest that you watch the first video. I'll have it linked in the description on YouTube. This video is going to contain a little bit about ASME Y14.5, but we're also going to take a small step back and we're going to go over some useful material that we might need to know before really digging deep into GD&T. As this is a chapter focused on manufacturing, there'll be a small hint of design for manufacturing and assembly, otherwise known as DFMA. This is all stuff that I think you should know before diving deep into ASME Y14.5. Okay, so let's start with technical drawings. We all know what a technical drawing is, right? There are many different types of technical drawings, but I would say the two most common ones, at least for mechanical engineers, are the detail drawing, which is what you see on the screen here, and the assembly drawing, which is often shown with an exploded view. This detailed drawing example that I put together is one that I adapted from a company called Tarka, which is an engineering firm based out of Boston, Massachusetts. They have a really great video called How to Make Prints a Machinist Will Love. It's a fantastic video if you want to know how to make really high quality engineering drawings. I really strongly recommend watching that video. Anyways, moving on. So in general, technical drawings must contain a complete description of an object's shape, a full description of its size, and as a reminder, those are two separate things. The shape is more the geometry, and the size is more like its scale, the scale of the geometry. And it must contain all information that may be necessary for manufacturing. To be clear, that does not mean you want to specify entirely how you expect the part to be manufactured. In fact, it's best to leave how a part is manufactured to the shop. Generally, you care about the what, but not the how. But sometimes, for example, if you know for sure you want an anodized aluminum part, you do have to specify a little bit of the manufacturing. So in this case, you would specify a standard that you expect the part to meet for the anodization on the drawing. I left a small example here of what you might see on the drawing, but all in all, in a nutshell, a technical drawing must represent the object in its final form. In general, the standard to follow, in North America at least, is usually ASME Y14.100. The standard serves as a guide for how technical drawings are to be structured, revised, and managed. So let's go into linear dimensions. When it comes to linear dimensions, the ASME Y14.5 standard contains strict rules for formatting of the decimals based on which units are used. So for metric units, such as for millimeters, a leading zero before the decimal point is mandatory. Whereas for imperial units, such as for inches, a leading zero before the decimal point is omitted. There is no zero before the decimal point. ASME Y14.5 also supports two ways of doing angular dimensioning, which is decimal degrees and DMS, although really, in my experience, you only really see decimal degrees. DMS is an acronym for degrees, minutes, and seconds. DMS is sometimes used for high angular precision applications instead of decimal degrees. It can make doing mental math easier since we're already used to doing similar math for time. There are 60 minutes in a degree and 60 seconds in a minute. So in a way, you can kind of think of degrees as being analogous to hours. Okay, so what does ASME Y14.5 say about dimensioning profiles? Now, this is something that I personally was puzzled before learning about Y14.5 about how you're really supposed to dimension, let's say, organic geometry or some complex shapes on a drawing. And And I believe the answer is, I believe the oldest way to do it is what you see on the drawing here. It's with baselines. Um, and this is supported by the Y14.5 standard. You can do it. Basically, you select points along the curve and you dimension them using baselines. But I wouldn't recommend this because you can end up with a completely different curve than what you might expect, especially since the position of the curve between each point isn't clearly defined. Alternatively, you can provide a mathematical equation that defines the curve. You might do that, for example, I don't know, for the profile of an airfoil. Um, this equation-driven dimension would be considered a basic dimension, which we will get to later. You need GD&T to tolerance basic dimensions. But what is the most common way to dimension profiles nowadays is just to provide the CAD file or a 2D file or some sort of reference file and make a reference to it in the notes. So for 2D, a file such as a DXF file would work. You can provide for 3D a SOLIDWORKS file, although I would personally recommend a step file, which is an open format. IGES is another open format, which is also an option. You might make the reference, for example, by putting a note on the drawing saying untolerance dimensions are basic per the digital data set. You can also refer to the file format if you want things to be clear. So in here, I put the reference step file, but that doesn't really matter too much. What matters is that you clearly say that the undimensioned dimensions, the untolerance dimensions are basic, and to make a reference to a file. And again, yes, so I mentioned basic. It's the same thing. We'll get to how GD&T can tolerance these basic dimensions later. So I'm going to do a small review of dimension terms. These might seem pretty obvious, but I really think it helps to go over them. The nominal dimension is just the regular dimension value. So for a dimension of 10 millimeters plus or minus 2 millimeters, the nominal dimension is just the 10 millimeter part. It's often also called the basic dimension, but basic really only applies when no linear tolerances are given. And again, we'll see later how basic dimensions work. The dimensions with the tolerances applied are often called the limit dimensions. So the limit dimensions are the dimensions with the plus dimension or the minus dimension applied. There are two of them, the minimum limit and the maximum limit at both bounds. And the mean dimension is exactly midway between both limit dimensions. It's the average of the two limit dimensions. So in this particular example, we have our nominal dimension here, which is tolerance plus 0.06 minus 0.02. The minimum limit is minus 0.02. So it's the nominal dimension minus 0.02. And the max limit is the nominal dimension plus 0.06. And the mean dimension is right between both of them, so it would be plus 0.02 in this particular instance. So let's move on to tolerances. I assume we all know what tolerances are, but why do we care so much about tolerances? Well, it's because of interchangeable manufacturing. Every time you take your car into a shop for repairs, you're relying on interchangeable manufacturing. Parts can be made from all over the world, and if tolerances aren't controlled well enough, your brake rotor mounting points, for example, might not align with the wheel hub. Notice how many parts there are in this example of a rear suspension assembly. Also notice how distributed the manufacturing is. It's all over North America. So we have Michigan, we have Kentucky, we have North Carolina, we have Ontario, Canada, we have Monterrey, Mexico, Michigan, Indiana, Coahuila, Mexico, Ontario. It's all over North America. If one singular part has their tolerances off, problems will show up in assembly and it'll often halt that assembly line. The problematic parts often have to be scrapped and replaced with new ones. This is all very expensive. It's usually cheapest to make sure that your parts are toleranced correctly at the design stage and inspected before being sent to assembly. And same as in the last chapter, I had to use an AI generated image to avoid licensing issues. But the Automotive Parts Manufacturers Association has a diagram which is very similar to this. If you Google Automotive Parts Manufacturers Association rear suspension assembly, you'll get an image that looks almost identical. So you might think then, let's just make our tolerances super tight and not worry about tolerances at all. Well, now your assembly costs 4 times what it should. Machining operations have costs. As you tighten the tolerances, the cost of machining your part increases exponentially. So realistically, you should set your tolerance requirements to be as low as you can while still meeting your functional requirements. Those functional requirements are often informed by any jigs that are needed for manufacturing, any fixtures in assembly, or any gauges in inspection. So, for an example, locators on fixtures are often designed with 20 to 50% of the parts tolerance, so it's much stricter. And for go no go gauges is 10% of the parts tolerance. That is 10 times tighter tolerances. This means that you have to also factor in the manufacturability of your jigs, fixtures, or gauges. So if you have a tolerance of 5/1000ths of an inch for a feature, your inspection gauge has a tolerance of 5/10,000ths of an inch. Is this gauge reasonably manufacturable within your budget? Do you even need a go no go gauge? For a jet engine component, yeah, that makes sense. It's exposed to high stresses and high forces, and it's a safety critical component. That makes sense. But for a children's toy, well, you certainly don't need such tight tolerances, and you wouldn't even need to inspect a toy with a gauge really either. These factors all have to be taken into consideration. On the right, you can see the costs for machining parts with specific tolerances along with their respective machining operations. And this is for steel, but it's basically the same thing for other materials as well. Tolerances, this is a really important part, and it'll show up later. Tolerances can also accumulate. So in the middle here, you can see here that I've set for dimensions with 2 decimal points, the tolerance is plus or minus 0.05. Now, normally you would put this particular this particular note in your title block, but obviously this is not a drawing, so I put it here for convenience. And on the left, you can see an example of chain dimensioning. So each dimension is chained one after the other. The overall length, or height in this case, of the part can vary by 0.2 millimeters, even though the individual tolerances are set to 0.05 millimeters. This is because there are 4 dimensions with a tolerance of 0.05 that can accumulate. So 0.05 times 4, that's plus or minus 0.2 millimeters. On the right, you can see an example of baseline dimensioning. So they're all dimensioned from the same point. And the overall height or length will never exceed 0.05. These tolerances do not accumulate. Now that doesn't mean that there isn't a time and place for chain dimensioning. Chain dimensioning is generally not recommended for most applications. Baseline dimensioning is usually a lot better. But that doesn't mean there's not a time and place for it. It really depends on what dimensions matter the most for your functional requirements. The placement of dimensions tells machinists and inspectors what sections of your part matters the most with respect to size. So what matters the most is, does it matter more that each one of these be exactly plus or minus 0.05, or does it matter most that each one of these be 0.05 from the bottom, it means something completely different. It communicates design intent. But, in most situations, chain dimensioning is frowned upon. All right, moving on. Tolerance accumulation can also happen in assemblies. And this problem can get really bad if your assembly has a very large number of parts. But here I'll use a simple example. Let's say we have 4 blocks, each with a nominal dimension of 24.7 and a tolerance of plus or minus 0.2 millimeters. We also have a part with a slot, and this slot is dimensioned at 100 plus or minus 0.5 millimeters. We need there to be clearance between the 4 blocks and the slot, or else the blocks just won't slide in. Well, the best case scenario with our tolerances is where the slot is at its max limit dimension, so 100 plus 0.5, so that's 100.5 millimeters, which is its max limit, and the blocks are each at their minimum limit dimensions, where they would accumulate to 98 millimeters. And in that situation, there remains 2.5 millimeters of clearance, which is perfect. They'll slide in no problem. But what happens with the worst case scenario? Well, that's when the slot is at its minimum dimension, which is 9.5 millimeters, and the blocks are each at their max limit dimensions, which is where they're at. They accumulate to 99.6 millimeters. You'll notice that 99.6 is larger than 99.5. That leaves us with 0.1 millimeters of interference. Those blocks won't slide in freely. You have to take assembly tolerance accumulation into consideration, or else you could end up with situations where parts don't fit where they're supposed to. And we can't really talk about tolerances without also talking about the systems of limits and fits. If you ever asked yourself, what tolerances should I set, especially for like holes, or what size differences should I set for holes, shafts and holes? Well, that's what these systems are really useful for, the systems of limits and fits. There are 2 main systems. Well, actually there are 3 technically, but at least in North America, well, and worldwide actually. But one of the 3 is really just a copy of what the other. The 2 main ones are ANSI B4.1 for imperial, so inches, and ISO 286 for metric. The other metric one is ANSI B4.2, but that is the copy. That one is a very similar copy to ISO 286. They're not exactly the same, but they're very compatible. Parts designed to ANSI B4.2 specifications are almost always interchangeable with those designed to ISO 286 specifications if the same tolerance classes are selected. Both systems have preferred fits to select from the list based on your particular application. So if you can, it's usually best to select from a standard list of fits based on your application. That's why you're using the system in the first place. And similarly, if you're buying a part, they'll often specify what fit that part is supposed to work in. So like if you buy a bearing, they'll often say your internal feature, your hole has to be to this particular fit. It's also very, very strongly recommended to use the preferred hole size, although it's not required, as those use standard drill bits, and they don't require extra operations that would drive up the costs. This really helps to keep machining costs in check. So let's look at a few of these fits. I won't go through all of these, and there's way more than what I even have on the slide, but if you want to read what I have here, you can pause the video. I'll go over a few of them though. A fit that I'll bring up later, in a later example, is the RC4 or H8/F7 close running fit. RC4 is the imperial version, and H8/F7 is the metric version. It's often used, this particular fit, these fits are often used in journal bearings that run at moderate speeds. Another fit example is the LT3 or H7K6 fit. This allows for parts to be located with no perceivable play, and you would normally use this when parts need to be assembled by hand or with minimal hand tools, such as with a rubber mallet. This is a transition fit, so there may or may not be interference, but there's usually a little bit of interference. Like it won't slide in freely, and that's the point. You usually pick that for that reason. Um, the fit is semi-permanent, and it usually can have parts assembled or disassembled with a rubber mallet. Lastly, an FN2 or H7S6 press fit is often used for high torque applications, such as coupling a flange and a shaft together. And this fit is permanent. It cannot be disassembled without damage. Now these like high interference fits usually require like heat treatments or cold treatments, I think, to be able to get them to fit what would normally not slide in regularly. So, and the very last thing I want to talk about is surface finish. I won't go too deep into surface finish, but you can think about it as being very similar to the tolerance on a micro level. Generally, in North America, it's controlled by ASME standards, both the Y14.36 and the B46.1 standards, which go hand in hand. For most situations, I would recommend setting in the title block a default surface finish of 125 microinch RA as to not drive up machine costs. Over constraining the surface finish can drive up costs in the same way that over constraining tolerances do. And in case it's not clear, surface finish, putting a tight surface finish is kind of akin to polishing it, having a more polished surface. A really good example of an application of a surface finish is with journal bearings. So that it was that particular previous RC4 fit that I mentioned with the journal bearing. Um, the journal is often much harder than the bearing itself. So if the journal has too rough of a surface finish, it'll act like a file and it'll penetrate the lubricating oil film and wear away the softer bearing material. So if to avoid that, you can set a finish of 16 micro-inch RA on the shaft's surface, right where the journal rotates in the bearing. And that's it for now. I think in the next video, we're going to go over some fundamental concepts of GD&T. But for now, that's all I have. And as usual, these are my sources. Thank you very much.